In relation to number 39, we recall that log x is the function that's inverse to 10 to the x. So if we have a graph of y equals 10 to the x versus x, this is what we get for a table with x values from -2 to 2 running by integer values. To get a table for the log of x, we simply invert the two columns so that this column becomes, the y column becomes the x column becomes the y column, and then we have at least a partial table for y equals log of x. So a log to any base is obtained by inverting the columns of the table by switching the x's and the y's. This means that if we have a typical exponential function, we get the log function by switching the x's and the y's. If you do this and think about what's happening, you see that what you do is you're reflecting each point here across the y equals x line to an equal distance on the other side, moving the point at a perpendicular straight across the line, so that the log graph is going to be a reflection of the exponential graph across the y equals x line. And if this is a graph of 10 to the x, then this is a graph of the log of x. If this is a graph of e to the x, then this would be the natural log. If this was 5 to the x, this would be the base 5 log of x. Number 42 deals with trigonometric functions. To get the graph of a sine function, we think of motion around a reference circle with period t starting at some angle theta naught, and also a radius a for this reference circle. Okay, so if this reference circle has radius a, period t, and starts at theta naught, then as we move around the reference circle, the y-coordinate first starts by going up, so the graph starts by going up slightly. Then it goes down to a minimum, so the graph will go down to a minimum. Then it comes back up to a maximum, and so forth, starting at whatever value of y corresponds to the angle in the radius. The period t is such that in time t we go through a complete cycle, meaning a complete cycle around the circle, a complete revolution around the circle. Now, a complete revolution around the circle is a change in angle, and let's call this, okay, we're graphing the y-coordinate versus t, time t. The angle has to change by 2 pi when we change t by a period, which means that if our time little t was equal to a period big T, then we would have to get 2 pi when we multiply 2 pi over big T times that t. That means that we have to have a 2 pi over big T out in front here. The only thing we can have out in front to accomplish a complete circle in time big T is a 2 pi over t. Then when little t changes by big T, the angle changes by 2 pi, and we do go around the circle once. And then of course we add theta naught to the end, so we have y equals a sine of 2 pi over big T times little t plus theta naught. And that's the graph that we're going to get that corresponds to these parameters. Another useful picture, number 43, corresponds to the inverse function, inverse sine. If we have a y and we want to find the inverse sine of y, that means the angle whose sine is y. We construct this on a circle of radius 1, a unit circle. We find the position of the coordinate y, and we project that over to the circle. Then the angle that we get here is the inverse sine of y. That is, well, there are two possible angles. There's an angle over here and an angle over here. The one that lies between negative pi over 2 and positive pi over 2 around the circle is going to be the inverse sine of y. The inverse sine lies between negative pi over 2 and pi over 2. if we draw the graph of the inverse sine, we confine our attention to the values of the angle that lie between negative pi over 2 and pi over 2, and we simply reflect the graph through the y equals x line, so that if the sine function acts like this, the inverse sine function is going to look like this.